Power is then the work done per time. How much work is being done divided by the time over which that work is done. We can also think of it as an energy per time. How much energy is changing or energy is doing something per time. We'll use the symbol capital P for power. So power is work over delta T, W over delta T. Remember, that's work in this case, not weight. The units of power are then the units of work over the units of delta T. The units of work, remember, units of work, not weight, are joules. Units of delta T, seconds, joules per second. And again, that combination of units is something that we will see so often that it has its own name. 1 joule per second is a watt. This is kind of an interesting unit because this is one of the very few SI units that's in common usage in our country today. Our country, in the United States anyways. I'm not sure where you are, but in the United States, today, a watt is one of the few SI units that's commonly used. Not the only one, but one of the few. And I'm very, very sorry about this, but the symbol that we use for watts is capital W. So, again, please don't confuse the capital W when we mean it to be for watts as when we mean it for work or weight. So, in this case, 1 joule per second is a watt. If you have a 60-watt light bulb, for example, what does that mean? That means that light bulb is using 60 watts or 60 joules per second. That's the amount of energy per second that it's using, the electrical energy that it's using. Unfortunately, it doesn't mean that it's producing 60 watts of light per second. It's how much energy it's actually using. The efficiency of light bulbs is typically much, much less than 100%. So the amount of energy actually being produced as light is typically much less than 60 watts. Some types of light bulbs are more efficient, like LED light bulbs are much more efficient. They produce more energy as light than say an incandescent light bulb, which produces much less light per joule used. It's kind of interesting, another very commonly used unit are the units that electrical energy bills are often given in. If you have ever paid an electrical utility bill, the units that are used to measure how much electrical energy you've used are, do you happen to know this? They are kilowatt hours. So what is a kilowatt hour? Well, that unit is a product of a kilowatt times an hour. So what is that? Well, what's a kilowatt? A kilogram means 1,000 of those things. So that's 1,000 watts. So a kilowatt would be 10 to the 3 watts. And a watt, remember, is a joule per second. So I'll just write that watt as a joule per second. What's an hour? An hour is 60 minutes and every minute is 60 seconds. So 1 hour is 3,600 seconds. So this is times 3,600 seconds. Notice the seconds cancel out. Multiplying this all out, what do we get? We get 3.6 times 10 to the 6th joules. In other words, 3.6 megajoules, million joules. So 1 kilowatt hour is an energy, and it's an energy of 3.6 million joules, 3.6 megajoules. So that's also actually a metric unit. It's not the standard form that we would usually think of in terms of, say, just joules, but we can very easily convert it to a standard SI unit, 3.6 times 10 to the 6th joules. Very, very good. So let's stick some numbers in here and try and use this result on a problem. Let's imagine that we have a car with a mass of 900 kilograms. That's a total mass, so that's the mass of the car with the driver. That is initially at rest, so V initial is 0. It speeds up, and let's assume it speeds up under a constant force, a uniform acceleration, to 20 meters per second, and let's say that it takes a time of 5 seconds to do that. Let's figure out how much power the engine has to exert in order to speed up the car. We'll do this actually in a couple of different ways. We'll figure out how much work is done by looking at the change in the kinetic energy. from the work energy theorem, we can figure out how much work was done. And then we'll look at it in a different way. The initial kinetic energy we know is 0 because the initial velocity is 0. The final kinetic energy we know 1/2 mv final squared is 1.80 times 10 to the 5th joules. The initial kinetic is 0. The final kinetic energy is 1.8 times 10 to the 5th joules. How much work was done? Well, final kinetic minus initial kinetic is just 1.80 times 10 to the 5th joules. That's the total amount of work that's done by the engine in accelerating the car, assuming no other work is done by non-conservative forces. That's an approximation. What's the power exerted by the engine? And let me just say this is an average power for a second. We'll see why this is an average power in just 1 second. That's the work per time, which is 1.8 times 10 to the 5th joules, divided by the time, 5 seconds, and we get 3.60 times 10 to the 4th watts. That is the average power output for the engine accelerating the car. Why do I say the average power? Let's think about this just for a second. The power is the work per time, work W over delta T, and the work is F delta R cos theta. Well, let's look at this. We've got F delta R cos theta over delta T. What is delta R over delta T? That's the velocity. That's the displacement over the time. That's the velocity, or the speed, the magnitude of the velocity. So we can write the power as F times V cos theta, where theta in this case is the angle between the force and the velocity. What's the force acting on the car? As I said, we'll assume the acceleration is constant. We can say the force is the mass times acceleration, or the mass times delta V over delta T, which is 900 kilograms times, it goes from 0 to 20 meters per second. So delta V is 20 meters per second, delta T is 5 seconds. Multiplying that out, we get a force of 3.6 times 10 to the 3rd newtons. The initial power is F times V initial cos theta. But what is V initial? Initially, the car is not moving. So the initial velocity is 0. The initial power is 0. But the car is speeding up. The final velocity is 20 meters per second. So what's the final power? The final power will be the force times the final velocity cos theta. The force is 3.6 times 10 to the 3. The final velocity is 20 meters per second. Theta is 0 because the force pushing the car forward is in the same direction as the velocity, so the angle between them is 0, and we get a final power output of 7.20 times 10 to the 4th watts. The initial power is 0 and the final power is much larger. It takes more power to accelerate the car because it's moving more power to accelerate the car when it's going faster. Because it's moving faster, delta T is smaller for a given delta R than it is initially. It will go 1 meter in a longer time initially. It'll go 1 meter in a much shorter time finally. So we actually have varying power as the car accelerates. What's the average power? If we take an average of 0 and 7.20 times 10 to the 4th, we get 3.60 times 10 to the 4th watts. We get exactly the average power we got in the first case. Very, very good. Excellent. We have been talking about some different kinds of energy, work being done. We've talked about kinetic energy. We've talked about potential energy. Are there other kinds of energies? How do all of those things fit into our conservation of mechanical energy? Let's take one quick look at that before we finish. We have talked about kinetic energy, energy of motion, gravitational potential energy, energy that something has because of its height in a gravitational field. But actually there are many, many other kinds of energy. We mentioned the potential energy stored in a bending pole vaulter's pole. There are energies stored in springs. There are chemical energies, energy stored in chemical bonds and molecules. There's nuclear energy, energy stored in the nuclei of atoms. There's thermal energy, which is another kind of kinetic energy and energy of motion, but a more random type of kinetic energy that objects have that make them hot, or lack of energy making them cold. There's energy in light, electromagnetic energy. There are many, many kinds of energy. If we think of all of them together and we consider every possible kind of energy, then we have one of the most fundamental laws. Sometimes it's referred to as a law, sometimes it's referred to as a principle, that there is in physics. It's called the conservation of energy. And it states, energy can neither be created nor destroyed, but can only be converted from one form to another. In other words, if you consider all the possible kinds of energy, whatever amount you start with is the same as the amount you end up with. The final amount of energy is always the same as the initial amount of energy. You can convert it from one kind to another, but the total amount is always the same. If we go back to my analogy with the money in your pocket and the money in the bank, if you think about the money in your pocket as the kinetic energy, the money in the bank as your potential energy, you might have a job and get some energy from some money from another source, and you might spend it. But if you count up all of that total energy, wherever it went to at the store, whatever it gained from a job or whatever, the total amount is the same. Now that analogy doesn't go completely 100% all the way, because money is constantly being minted and things like that, and money is destroyed by the mint, stuff like that. But don't take it too far. But the idea is, if we consider all of the kinds of energy, the total amount remains the same. How does that work in terms of some of the problems we've looked at with kinetic energy being lost to, say, work done by friction or something like that? Well, you can do a very simple demonstration. I'll take some kinetic energy and turn it and lose it into thermal energy. If you take your hands, put them together, and just rub them very briskly like this, you can feel your hands getting warmer. Why is that? Because the kinetic energy of your hands is being lost to the frictional work done between your hands, and it's turning that kinetic energy into thermal energy, which you can actually feel as an increase in temperature in your hands. If you take that kinetic energy initially and add it to the thermal energy initially, you'll get the final kinetic plus the thermal energy final. The total amount of energy still stays the same. You might have to take into account some energy that was lost when I actually put my hands together. I made a little sound. Well, that sound carries some energy. You actually can see my hands. Maybe there's some energy being lost from energy coming off from thermal energy from the fact that I'm actually producing some thermal energy in my hands, turning it into not thermal energy, sorry, electromagnetic energy. But if the bottom line is, if you take all of those energies into account, the total amount remains the same. The total amount of energy is conserved. A very, very fundamental idea in physics. Very, very good. Next time, we're actually going to start to take a look at some new concepts, momentum and impulse, and we'll see that actually there's another quantity that's conserved. Actually, in physics, there are quite a few conserved quantities, and we'll start taking a look at another one next time. Well, I hope you enjoyed that. I'll see you then.